Make sure it hears me. Yes, it's good. Good. Okay. All right. Welcome to the end of chapter 2. So next Monday we'll be reviewing. So in essence, I'm going to go over the homework assignment that you have due next Wednesday. And then next Wednesday will be your test. So I should be able to be here about 9 o'clock. I'll run over here around 9 o'clock on Tuesday. So you can come in a little bit early if you want to start your test. And I'll be here till 11:30. So you have a couple hours to do your test on Thursday. If you have the extra time built in your schedule and your work schedule and stuff. Any questions on what we've covered so far that you want to ask before we get started in the infinity limits? Okay, so after I go over this, you should be able to do all the problems on the homework. I know there was a couple ones with limits to infinity. So, all right. So, in pre-calculus, you actually already did this. Well, to a point. Who remembers how to find horizontal asymptotes? So, all right, who remembers what a horizontal asymptote is? Okay, what's a horizontal asymptote?
Basically, a value that it will get infinitely close, but it will never pass the beyond.
Okay. Yeah. Yep. That's a vertical asymptote. That's how you calculate it. Yeah, that's one of the ways you calculate it. So if we look at the first one. So let's look at this. So here's my first equation. So the horizontal asymptote is, if we sat there and zoomed out, what's the equation getting really, really close to? Yeah, so in this case, as we go further and further out, you can see it's getting closer and closer to y equals 0. Now, one thing that some people say and believe, which I want to dispel that piece, is that the value can never equal that. That's not true, because it equals 0 right there. So your function can cross the horizontal asymptote. That is possible. What the horizontal asymptote's looking at is what's going on as we're going, as in essence, x is going to infinity, or as x is going to negative infinity, which is where the limits come into play. Because remember, I can't necessarily find exactly what this is going to equal at infinity because I can't plug in infinity. Infinity is not a number. So we're looking at the limit as x goes to infinity to figure out what it comes to. So in pre-calculus, you did this. You were looking for horizontal asymptotes. And the way you did it was to look at the degrees. So if the degree was bigger on the bottom than on the top, my horizontal asymptote was y equals 0. Okay, because my degree on the top is 1, my degree on the top is 2. If the degree on the top was bigger, when you did it, it had no horizontal asymptote. If the degrees were the same, you looked at your leading coefficients. So in this case, my horizontal asymptote is 5/6. And the reason that's true is because the further you go out, the bigger those numbers are, only the highest degrees are going to matter. Okay? Because as you get bigger and bigger, this 2x isn't going to mean much. All right? But that x to the third is going to stay because that's the biggest one. And then in essence, those would cancel each other out because they're the same on the top and the bottom. So that's what you learned in pre-calculus. The rules actually don't change in calculus. The thing we're going to look at is we're going to look at a lot of different problems that this rule that you learned in pre-calculus might not work with. Okay, this worked really well when you were looking at just rational functions, when you were dealing with a polynomial over polynomial. If we're dealing with anything else, it might not work as nicely. So that's just an example of what a horizontal line. Yes. Sure. Actually, I'm going to delete that slide because we don't need it now. Oh, not that one. No problem. All right. So the horizontal asymptote is y equals L. And the limit as x goes to infinity of f of x equals L. And the limit as x goes to negative infinity would equal L. Those L's do not have to be the exact same thing. And as you can see in these two problems, they don't even have to go to that on both directions. So if we look at this first one, this is the one that has the limit as x is going to negative infinity. We have a horizontal asymptote. However, my right side, as x goes to infinity, this graph is going to go to infinity. Just keep going up. If we look at this graph, this is one of those ones that some people wouldn't expect to exist. Remember, I said it can cross it. It keeps crossing the horizontal asymptote. However, as it's getting further and further out, that oscillation is getting smaller and smaller. So it is still necessarily going to that horizontal asymptote. Okay. So this one would be like the limit as x is going to infinity. Yeah, that's negative infinity and positive infinity. Oh, no problem. I was writing on a slant for some reason. So this one's going to keep going. This one's basically going to keep oscillating and getting bigger and bigger, going in that direction. And it's getting smaller as it's going to the infinity on the positive side. Okay. We also could have a situation like this. The arctangent, oh, I can go back if you need it. So in each of these, we had one horizontal asymptote. However, the arctangent is a good example of two horizontal asymptotes. As my x goes to negative infinity of f of x, it goes to negative pi over 2. As my limit as x goes to positive infinity, it's going to positive pi over 2. So I can have multiple horizontal asymptotes, or basically two. It's one going one direction, one going the other direction. Yes.
Just describing what numbers it approaches.
Yeah, it's basically describing your end behavior. So if you remember in pre-calc, you're talking about end behavior. It's like typically like the odd ones goes up, goes down, those type of things. Horizontal asymptote is describing the end behavior as it's getting closer and closer to a value as it goes to infinity. So you're going to work a lot with going to infinity because that's not what I wanted to do. Let's try that again. Because as something gets infinitely smaller, infinitely big, or those type of things, strange things can happen, but it also allows me to cancel stuff out and eliminate things, which is going to be very helpful going forward. All right, let's look at a simple case. Let's just get a graph, and then we'll figure out some the asymptotes for it, and then we'll look at some equations as well. All right. So in this graph, is it big enough for everybody? I can kind of make it, I can actually make it a little bigger. I don't really need that. Yeah, a little better. Let's look at vertical asymptotes first. Do I have any vertical asymptotes in this problem? Okay, where's my first vertical asymptote? Yes. -1. So x equals -1 is a vertical asymptote. What would be the limit as x goes to -1 of f of x? That one would be infinity. Because both directions go to infinity, correct? Okay. What's another vertical asymptote?
X equals 2.
X equals 2. So what's the limit as x goes to 2 of f of x?
Does not exist because they
That-
go in different directions.
Right, that one does not exist because that goes in different directions. I could have the limit as x goes to 2 from the right and to the left. Those would exist. But the main limit does not exist in this situation. So I could have the limit as x goes to 2 from the right, and that's negative infinity, as x goes to 2 from the left, or from the right, actually, in this case. And that's positive infinity. I said it backwards. Okay. So those are my vertical asymptotes. Look at horizontal asymptotes now. So what's the limit as x goes to negative infinity of f of x? It's going to be 2. Because this side's getting closer and closer to the 2. What's the limit as x goes to positive infinity of f of x?
4.
That's 4. So I have 2 horizontal asymptotes here. I have y equals 2 and y equals 4 are my 2 horizontal asymptotes. We're going this direction, which means it's getting closer and closer to there.
When it asks you a question like that, you have to look at a lot of hands to decide.
We're looking as x goes to infinity. So we're going that direction. So as x gets bigger and bigger and bigger, what's this graph doing? It's getting closer and closer to that line, which is x equals 4, or y equals 4. We're going the other direction. Now, unlike any other point, like if I was looking at the limit as it goes to 2, like we did in this problem here, I'm able to look at it coming from the left, coming from the right. And as long as they go to the same place, that's going to equal. Infinity doesn't have, I can't go to the left to infinity and to the right to infinity. Because infinity isn't a number. It's going on forever. So you're not going to have that infinity minus infinity plus. You have negative infinity and positive infinity, which would be your 2 directions, but you're not going to have enough from that one. So you can't really split that one up. So you're really only looking at it in one direction at that point. Okay. Does that make sense? All right. Let's look at a couple problems. So 1 over x. So as we're going to infinity, So let's look at the first one. What's that going to equal?
Zero?
Why?
As it gets smaller and smaller and smaller as x goes to infinity.
So think about a fraction, right? 1/2, 1/3, 1/4, 1/5, 1/10, 1/100, 1/1000. What's happening to it? It's getting smaller and smaller. So as I go to infinity, as the bottom gets infinitely large, that's going to go to 0. And if we look at the graph, that's what we see. It's getting infinitely small. And it does it pretty quickly. Zoom out even farther, basically. It's pretty much 0 at that point. What about to the negative infinity? It's also 0. As it's getting closer and closer, it's going to be a negative number, right? However, as it's getting infinitely large on the bottom, that negative number is still getting closer and closer to 0. And we see that on this side. It's still getting closer and closer to 0. That right there is probably the most important thing we're going to figure out. Because if we're looking at an equation, what's nice about the number 0? It gets rid of things. So if I can have my function going to 0 or somehow creating it so it's going to 0, it can eliminate parts of my function that I'm looking at. And therefore, I don't necessarily need that piece. I can only look at what's left. So let's look at this one. Using your pre-calculus brain, what's the horizontal asymptote? 3/5. All right. Now I'm going to show you your calculus brain. My goal is to get these to use somehow the 1 over x to use this rule, because that goes to 0. So if I take a fraction and I multiply the top and the bottom by something, does it change the fraction? So if I have 4/5 and I multiply it by 2 over 2, is the problem different? No. As long as I'm multiplying it by 1, correct? Okay. If I had 10 over 32 and I divided the top and divided the bottom by 2. So it's 5 over 16. Does that change my problem? No. So we have confirmed that if I multiply or divide the top and the bottom by the exact same thing, my problem does not change, correct? Okay, good. So if I take 3x squared minus x minus 2 and divide it by x squared, and then I take the bottom and divide it by x squared, did I change my problem? No, because I divided the top and the bottom by the exact same thing, correct? Good. All right, so now let's look at the top and the bottom. So what do I have on the top now? All right, at 3 minus 1 over x minus 2 over x squared. And on the bottom, I have 5 plus 4 over x plus 1 over x squared. If I take the limit of this, what do I get? What's that 1 over x going to become? So I have 3 minus 0. 2 over x squared is going to become over 5 plus, which equals 3 over 5. Whole lot of work to do the exact same thing you did in pre-calculus. Okay. So, but that's the reason the rule that you learned in pre-calculus works. Yes. Yes, of course. Otherwise, I wouldn't show it to you. So, if I gave you a problem like that, using your pre-calculus brain, what's the answer? See now the problem? The rules that you learn in pre-calculus work really well for that. Okay? Polynomial over a polynomial. Really simple. Just look at the degrees, cancel the numbers out, you're good, you're done. I plugged in basically what's the limit as 1 over x goes to infinity. 0, right. That's why this rule right here and what we did here is so important, because that established that 1 over x is 0. And technically 1 over any x to any power is going to go to 0. It's just going to get there quicker. So the pre-calculus works really well when you have a polynomial over a polynomial, because you have your degrees, you have your numbers, it's easy to look at, you're good. Once you get to a problem like this, or a problem like this, or a problem like this, these type of problems, that rule doesn't work anymore. However, we still need to somehow figure out what the limit goes to. And I can't just plug in infinity, because if I plug in infinity, I'm going to get infinity over infinity. And that doesn't help me. Because you might go, oh, it's infinity over infinity, that's 1. But that's not always true. Yes. If the limit of a constant over x. So it can't be x over x, because that would be different. That's why if you looked here when we did it, we had x over x squared, which I reduced to 1 over x. We had 2 over x squared, that's fine. So 1 over x goes to 0. 2 over x squared would go to 0. It would actually go to 0 faster. Because it's now squaring those numbers. But it doesn't matter what number's on top. Because the bottom basically becomes so large it overwhelms it. Okay. So let's look at this problem. We're going to use the same rule. Okay, we're going to use that. We're still going to use that rule. The limit as x goes to infinity. Yeah, totally can't write right now. Is 1 over x goes to 0. We're still going to use this rule. The question is what am I going to divide the top and the bottom by? Yes. Huh? I haven't done anything yet. I wrote the bottom piece. That's it. What am I going to divide by? What do you want to try? All right, let's try x. So I'm going to divide the top by x and the bottom by x, right? All right. So I have the square root of 2x squared plus 1 over x over 3x minus 5 over x. All right. Now what do we want to try? The bottom I can do something with, right? The bottom's going to become 3 minus 5 over x. That's good. How can I do the top, though? How can I get rid of the square root? Yes. Okay. What do you mean by multiplying by x squared? Okay. So I still would have to do something, same thing to the top and the bottom of the original fraction. So if I multiplied the top by x squared, I'd have to multiply the bottom of the fraction by x squared, which is my 3 minus 5x, or 5 over x.
Or it's squared by it's squared the top square.
If I square a fraction, does that change my problem? Yes, because now I'm not multiplying the same thing by the top and the bottom. Can I somehow put that x inside the square root?
You multiply by the square root of x.
So is that true? I didn't change anything, right? That's literally just the exact same thing. So I can change my top to the square root of 2x squared plus 1 over the square root of x squared. Because that's the same thing, right? So I'm not multiplying or anything there. I'm literally just replacing it with something that's equal to. I'm basically unsimplifying it. Okay. And since I have a square root on the top and the bottom, I can now put it together. Yeah, this is still over that whole piece. I'm just literally looking at the top, and then I'll put it all back together. That's why I was doing it in a different color. So now this becomes the square root of 2 plus 1 over x squared. All right, so now let me put it all back together. I have the square root of 2 plus 1 over x squared over 3 minus 5 over x. Okay. So what do I have left on the top if I did my infinity rule that I know? I have root 2. What do I have on the bottom? 3. And that's my answer. Now you can see why your pre-calculus teacher told you that really understanding algebra was going to help you in calculus. And why I said at the beginning of the class, the biggest mistakes you're going to make is not calculus, it's algebra. Because you can start to see, like, everybody in here knows 1 over x is going to 0. That rule, you know, you could figure that out. You understand that. That's fine. It's how do I get this problem and manipulate it to a point where I can use that rule? That's the hard part. And that's all algebra. So that's that manipulation piece. It's like, how do you, looking at the blue one, like, how do you take over x and get it, basically unsimplify it? Because the first thing you would do if you had the square root of x squared is change it to x. So you need to kind of go backwards to put it back in there to be able to break this problem down. Yes.
The problem like this, could you just look at it and be like 2 over 3 with your other move?
Maybe. If you looked at this, would you recognize that the degree of the top and the degree of the bottom is the same? Right. You see them enough, you could, because the square root of x squared is going to be x. So it's, the degree of the top is 1 and the degree of the bottom is 1. So the rule does work for this one. Except it's just not something that you're going to instantly recognize like you would a problem like this. Okay. And in this situation, that rule would still work. In this situation, that rule will not work at all. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that division. Okay. So you can start to see how the goal is to get it so I can do that divi All right. Let's look at the next one. So if I plugged in infinity to this, which you technically can't do, but we do all the time, what's the square root part going to? That's going to go to infinity, right? What's the x going to go to? Infinity. You would think, but it doesn't work that way. I can't do infinity minus infinity. Infinity is not a number. You know that whole thing when you were a kid, you go infinity plus 1, infinity squared. Like, it's like that's how many times it said something. Well, those are all just infinities. We're all exactly the same thing. Okay? So I can't do something like that. So somehow I've got to change this problem to do something that I would know what it is. Okay? So somehow I have to manipulate this to get something else. So what would you like to try for this? We don't have a fraction, so I can't just divide the top and the bottom by something. Huh? Okay, how are you going to make it a fraction? Okay. Now I have a fraction. Okay. Is squaring it going to change my problem? Yes, so I can't swear it. So that's the thing. It's like when you're looking at things, and this is where your skills in algebra really come into play. You have to look for something that's not going to change the problem. But change it, well, that's not going to change the value of the problem, but it's going to change how it looks and works. So I can multiply by the top and the bottom. I can divide by the top and the bottom. I can't square the top and the bottom because that's going to change the problem. I can't add something to the top and the bottom because that would change the problem. And the same concept with subtraction. So really all I can do is multiply a fraction and not change the value. So I have a fraction now. We have it over 1. What's the next thing we want to try? And sometimes you're going to try things that just won't work. Okay, let's try to divide it by x, because that's what we've been doing, right? If I divided this by x, don't I also have to multiply by x? Because I can't change, that would, if I just divided it, that would change it, right? I could do the 1 over x on the top and the 1 over x on the bottom. I just don't know how much that's going to help me. Because that's going to, so I would have the 1 over x on the bottom now. 1 second. Over x minus 1, because now it's x over x. So now the bottom goes to 0, so now I'm dividing by 0. It still does. So it's changed it. That's not a horrible thing. But I still have something that doesn't give me a value.
1 over x.
Right. That's what I'm saying. Like that still doesn't help. Go ahead.
Can we make it into 2 separate fractions?
It already is 2 separate fractions. Remember the 1 I put there.
For the first step. Put it over 1.
I somehow need to make a fraction. So putting it over 1 was not a horrible thing. Recognizing that the actual fraction exists is a good thing. So let's think back to something that I've done in here. Yes.
No, it's a little bit of a dumb question. Are we hitting a roadblock because of the issue with this, or?
We're hitting a roadblock because the parentheses aren't causing the roadblock. We're hitting the roadblock because we don't have division. So I can't use my rule that I know. We are. Nope. There's something that I've done in here. Yeah. Yeah. Let's use a conjugate pair. Let's multiply the top and the bottom by its conjugate. Let's make this a fraction. So we're going to multiply the top by plus x, and then the bottom by. So let's just look at the top and figure out what that's going to equal. So I have square root of x squared plus 1 squared. And then I have minus x squared. Because conjugates make the difference of squares. So the middle term cancels out, so I don't have to worry about that. So I have x squared plus 1 minus x squared, which equals 1. So now I have the limit as x goes to infinity of 1 over square root of x squared plus 1 plus x. So I now have 1 on the top. And if I plug in infinity to the bottom is getting what? Its bottom is going to go to 1. Infinity, right? Because it's infinity plus infinity doesn't cancel each other out or anything else like that. So I have 1 over infinity, which is 0. So now that I have, so when we were looking at the rule, it was 1 over a variable in the denominator. So if I have a fraction and the top is staying constant and the bottom is getting infinitely large, it's going to 0. If we look at this problem here, I now have a constant in the top. My bottom has variables in it that are going to get infinitely large. So it goes to 0. Okay? Yes?
I kind of got lost. When you started writing what you want to left. Just like that.
So when you're doing conjugate pairs, the point is that it's going to create the difference of squares.
Right.
So the middle term is going to cancel out. So I have the x squared plus 1, the square root of x squared plus 1 times the square root of x squared plus 1, which is that squared,
Okay, so that's
minus the middle two terms cancel out. That's the entire point of the difference of squares. And then x times x is x squared. Square and the square root cancel each other out. The x's end up canceling each other out, so it ends up being this one. Now, that's not always going to be true. Like, depending on what that is up on top, it's not always going to come out to be 1. This one does come out to be 1 because of the way they set it up. So. Now, this is one of those ones that you couldn't use your pre-calc rule no matter what. It wouldn't have worked. Yes. The goal is to get it to be something with a constant over a variable. Because if I get a constant over a variable, the variable is going to eventually get big enough that the constant on the top, it's going to go to 0. That's your goal. That's why that 1 over x is so powerful. It's like if I get it to be a fraction, it's going to go to 0. It's going to cancel each other out, so I don't have to worry about it. Then I can deal with the other pieces that are still there. Okay?
if you know your rules, could you just look at it and be like, yeah, you conjugate and switch it over to 1 over the.
Well, the conjugate here does come out to be 1 purely because of that x. If this was x squared plus 1 minus 1, for example, the x squared wouldn't have canceled out. The x squared would have still been there. Right. So it's not automatic. So I will, and I did mention this in my pre-calc, I'm really good at, if there's a trick that always works, I will tell you. If there's a reason, if I'm not telling you something, that means it's probably not always going to work. And I have a tendency to not like those types of tricks because you end up having to remember more. Because now you're going to have to remember the trick and when to use it and when not to use it. So it's actually ends up being more work to remember that than just to remember what to do in the first place. So, like, that's why, like, some things, yeah, they're always going to work, but I'm going to tell you, just do this. So, this, if you see square roots and stuff like that, conjugate pairs are great ways to get rid of them. Okay? As long as you have the two pieces, because the goal is to basically use the difference of squares to do that. All right, let's look at this one. This one's a little different. Okay. This one's not necessarily going to use the same type of ways that we were doing the other ones. So, what's happening in here? So if you remember right, one of the things that we can do is we can basically move the limit inside and look at that. Okay. So I can do the arctan of the limit as x goes to 2 from the right of 1 over x minus 2. So what's that doing? So I can't just plug in 2, right? Because it'll be 1 over 0. So what's happening as that 2? So the number that I'm plugging in is getting closer and closer to 2 on the positive side. So 2.1, 2.01, 2. That side. Is it?
Going to infinity, right?
So yeah, it's getting closer and closer to 0 at the bottom. So if you have 1 over 0, you're going to what? Infinity. So this one was x minus 2, right? So if we're looking at this is my graph. We're coming from, because it was 2 positive, right? We're coming from this side. We're getting closer and closer to, in essence, infinity. So that piece inside, that goes to infinity. So now we can look at the limit as, I'm going to use a m because I don't want to use that. So arctan of f. So now we can look at it as that's going to infinity. So what happens as arctangent goes to infinity?
Don't we have to restrict it in the
We did this one. That's arctangent. What's happening is arctangent's going to infinity. It's going to pi over 2. So this one's going to pi over 2. So you can't, I know it's one of those things that we like to do. We like to plug in numbers. Mathematically, you can't. So notice how I wrote it like that and not like that. Will it come out to be the same? Yeah. The problem with doing that is you have a tendency to do things like we did over here, where you end up with infinity minus infinity and saying, oh, it's 0, which sometimes it is. In this case, it was, but it's not always. So that's why we write it as the limit as something's going to infinity instead of just plugging infinity into the number. Yes.
So if it was, the limit was, X goes to infinity, then would our end be good? Like, one word.
If the original problem
Yeah.
was limit goes to infinity, then you'd have to look for what the arctangent of 0 is. So if you had this problem, so in that case, as x goes to infinity, this piece in the middle is going to what? Because we still can do the same thing. We can still move the limit inside. That's now going to 0, which I can plug in. So what's arctangent of 0? 0. So that's fine. I can use 0. 0 is an actual number. So we could definitely do that. Okay. So you can start to see how we're still using those rules. We're still using that 1 over x. But now we're looking at it in a variety of different ways. And most of these problems, except for the first couple, the rules that you learned in pre-calc won't work anymore. So that's why it's like, it's nice when you can use it. It's a quick way to get the answer. It just doesn't work for every possible function. And we're going to get into a lot more functions. All right. What about this one? Give me 1 second. I want to give people a chance to think. I think you have a good idea of what the number is, but yeah. I'm going to give him a chance to answer first. What do you think it goes to?
I think it's 0,
Okay.
because it's never really. been definite.
So is it 0 or is it not 0?
I say it does not exist.
Okay. You're going to say 0? Why 0?
Because what is 1 over cosecant of x, x on the bottom, and x goes to, wait, yeah, that goes to 0. If it goes to infinity, there's x on the bottom goes to 0.
Because of our
I think
rule.
that is, yeah.
One of the.
Okay, okay.
But does cosecant of infinity go to 0?
I do not know.
Or infinity? That's the thing. So for what you said to work, you'd have to, because what you did is not wrong. That's the exact same thing. But for it to go to 0, you'd have to say that part goes to infinity. So do you know that? Okay. Yes. What do we got?
I said 1.
Okay. Why?
Like the what is it?
Yeah.
Circle could be bigger than 1.
Okay.
I don't know. That doesn't.
So
sound-
no, but it also could be -1, right?
why it says zero, because it's constantly going in between. one
All right,
and-
so this is one of those situations where understanding how things work and why this is why we do problems like this is it's to make you think and really get a better understanding of what you're doing. Okay, we're looking at, for in essence, the horizontal asymptote, right? We're looking at what's happening as the problem's going out to infinity. Okay, so sine oscillates, right? It goes between from 0 to 1 to 0 to -1 and keeps going back and forth, right? So the unit circle continues to do that, right? That's where we're looking at. If you, in essence, went around the unit circle an infinite number of times, would it approach a single number or would it just keep going around the circle? You're just going to keep going around the circle, right? So therefore, does it approach any specific number? No. So this limit does not exist. Okay, that is possible. Okay. So remember, you're looking at what it's going to. Now, we had one at the beginning, like this one, that oscillates. But notice how it's oscillating. It's getting smaller and smaller. Okay? So, in essence, if we look at it, that's like this, sine of x over x. And if we look, as it oscillates, it's getting smaller and smaller, closer and closer to 0. Okay, because the top is basically going to keep flipping back and forth based between like -1, 1 and those numbers, but the bottom, as it gets infinitely large, that top number is not going to matter as much. So the bottom gets bigger faster, and that's why it goes to 0. But in this situation where we're looking at just the sine of x, it has nothing to stop it from just oscillating. So if you keep going around the unit circle, you're just going to keep going around the unit circle. Okay, so this one doesn't exist. What's the limit of x to the third as it goes to infinity? It's infinity, right? Okay. What's the limit as x to the third goes to negative infinity? Negative infinity. What did you call that in pre-calculus? That was end behavior. Okay. Your even roots went to the same, your odd roots went to the opposites. Okay. Good. What about this one? Using your pre-calc brain, what does it go to? Yeah. Okay. Why? It's just a problem. What tells you the direction it's going to go, though? The leading coefficient, right? That leading coefficient, in this case, is a positive. So based on your pre-calc brain, that's going to go to infinity. Okay. If we were looking at this and thinking about, oh, let's plug in infinity, like we tried back in one of the other problems, you'd have infinity minus infinity, which equals 0.
Square minus.
Right. So, but it's still infinity. So this is, so now, so if we look at, so you can't do subtraction like that. However, I can factor out the x. So now I have infinity times infinity, which that I can do. Okay. So when we're looking at it in terms of multiplication, that does work. Like you can think about it in that terms. That's going to go to infinity. That's going to go to infinity. So therefore, the entire problem has to go to infinity. Okay. I wanted to show you this one because when we look back at this problem, if you remember right, it was infinity minus infinity, and we got the number 0. Okay. And that limit actually did come out to be 0. So I didn't want you to have that thought in your head that, oh, actually, I probably can just do those subtractions. That's going to work, because it doesn't always work. And this is a great example of where it doesn't work. Okay. So this is one of those ones that your pre-calc brain was correct in thinking about limits in terms of that. It's going to go to infinity. It's going to go to infinity. All right. What's this one going to go to?
Does not exist
Why?
because the leading, I'm sorry, the degree of the numerator is greater than the denominator.
Okay. So what's the limit going to? I didn't ask what your horizontal asymptote was. You're right. Your horizontal asymptote doesn't exist.
That
It's okay. There's always reasons for my wonderful questions. It's to break the little habits that form in your mind. So what would I divide them all by? Okay. So divide everything by x. So I have x plus 1 over 3 over x minus 1, right? So I have x plus 1. If I do this and I'm looking at going to infinity, that's going to go to 0, right? So then I have basically infinity on the top over -1. Correct? So this is going to go to negative infinity. Okay. So while it doesn't have a horizontal asymptote, I'm looking for what the limit's doing. In this case, this limit's going to a negative infinity. Why didn't you divide it by x squared? Why did you divide it by x? Okay. So when you're looking at, this is a good example of trying to figure out what you're going to choose to divide by. Yes.
What's the concept of that? Is it divided by square, still be a square, right?
If I divide it by a square, I'm going to have a constant on the top. But if you look at what's going to be left on the bottom, so let's say I divided by x squared. I would have ended up having 1 plus 1 over x, 3 over x squared minus 1 over x. What's the bottom now going to? 0. The top's going to 1.
Which means you have to, like,
So now, right. So now I can't divide by 0. So when you're choosing your number, you're looking for the highest degree in the denominator. Okay. So in this case, that's why I'm dividing by x, because that's the highest degree in the denominator. In this one, I divided by x. That's the highest degree in the denominator. I don't want my denominator to go to 0. So if you divide by a degree that's higher than the denominator, your denominator is going to end up going to 0, and then you're stuck. So when you're choosing your number, you're going to look at your denominator and divide by that, the highest exponent in that one. Okay. In this case, that's the x. All right. Your turn.
and I know it's not part of the question, but when it goes to negative infinity, it goes to positive. The number goes to positive infinity, right? Like as x approaches negative infinity,
Oh, the other direction?
because you would just flip the infinity sign, right?
Yeah. So the bottom is going to be, yeah, the only thing that's going to change is the top. So it'd be going to positive infinity. Yeah. Let me just make sure. I'm almost positive this. I'm just going to graph it to see. Yeah. So actually, here's a good example of when you're looking at your. So this is the graph of that problem. If you were looking at just this, now this is just the home, so negative 10 to 10, 10 to 10, which is what you'd look at. What do you think the end behavior is doing?
How many double, like they both have two,
It looks like it's going to what? Infinity, positive infinity, right? There's the other problem. And actually, in this one, if you remember back to pre-calc, this one has the slant asymptote because the degree is exactly 1 higher than the bottom. So if you do your long division, you could have figured out that slant asymptote there. But that's one of those ones where when you're looking at just graphing it, a lot of times you just look at this. Sometimes zoom out a little bit and you'll see the rest of the problem. All right. Yeah, it's just a U instead of an X. All right. Find me this one. Who has an answer? Is this a polynomial over a polynomial? Yeah. Your pre-calc brain can kick into this one if you wanted to. Your leading code. So my degree on the top is going to be what? What's the highest degree I'm going to have on the top? 4, because u squared times u squared, right? What's the degree on the bottom? Also u to the 4. So what's the leading coefficient on the top? What's the leading coefficient on the bottom? So the answer is 2. Here is the calculus way to look at it. So they're dividing the whole problem by u to the 4th. So they FOILed out the bottom, divided by u to the 4th. The top, they didn't FOIL it. They just divided each one by u squared, because u squared times u squared is u to the 4th. So this way it saved them a little work on the top. But it still comes out to be 2.
Oh, since you know that they.
Yeah. All right, try this one. What's the degree of the top? What's the degree of the bottom? So this just goes to -1. Really? There we go. All right, now let's do ones that you can't do that way. Now you have to use your calculus brain. Yeah. Because the question is, how do you know that goes to You're not divided by X. Yeah. So. It's not divided by X. Okay. Remember, when you have a fraction, like two things under a fraction, you can flip flop. If it's divided by X, two. Good. I gotta keep going. Good. Everybody's got the kind of good beats down. That's plus. Good. I gotta keep going. Glad to luck. Well, you actually know the answer before I gave you the problem. Oh, you made a mistake. That's Mark's script. Oh. You go. You're good there. Okay. No, you do have to. That's not too bad. Two extensions. That'll help you out. You get to that point, I gotta figure out somehow to deal with that X still there. It's like all that algebra that she's like, I guess I'm going to calculus, I don't have to deal with this anymore. Oh, no.
Oh, it's not X, it's radical X squared.
Which is still X. All right. Most people got the conjugate pair part. And got to this stage. Most people got to that stage. So the question is what am I don't have, like, if I plugged in infinity now, I'm still going to get infinity over infinity. Well, actually, in the bottom, I'm going to get infinity minus infinity, which is 0. So either way, it's going to screw me up. So we want to divide by the highest degree on the bottom, right? What's the highest degree on the bottom? But it's under a square root. So it's x. So I'm dividing everything by x. So divide that by x. So the top becomes x. I mean, sorry, just 3. Because I have x divided by x. The negative 2x becomes just negative 2. And remember, to bring this inside the square root, I have to bring it in as an x squared. So 4x squared divided by x squared is 4. And the 3x divided by x squared is 3 over x. So can I do the square root of a negative number? No. When I take the square root of something, so if I took this, what's the square root of 25? Almost. Or negative 5. So the question is, how do you decide which one you do? So we're going to negative infinity, right? So since we're going to negative infinity, I want negative answers. That's where it becomes a negative square root of x squared, not the positive version of the square root of x squared. That's where that negative sign comes from. Okay. So remember, when you take the square root of something, because we're, in essence, we're changing x to the square root of x squared, but it could be negative square root of x squared, depending on the direction we want to go. Since we're going to negative infinity, we want the negative sign there. So this one ends up going to negative 3/4.
I got all the way up there and
I missed that.
that's the next.
Yeah, that's, it happens. That's all right. Let's do.
Can we go back to that for last one for a second?
Sure.
I'm sorry.
No, you're fine.
Where did the negative sign in front of the,
Okay.
where does it come from at the end there?
All right. So we say that that's that, right?
Yeah.
But it's not. It's that.
Oh,
Since we're going to the negative infinity, we want to use the negative version. That's where that negative sign comes from. It's fine.
why do we put it at the end? They want it-
We didn't. We basically put it in when we changed. So this square root, that x, moved inside. So that's when we did this step. So that's when we put in these the negative sign. Possibly. Honestly, I haven't made the test up yet. So all right. Last one, I'll work with this one with you because this one's not quite the same. That is an E. All right, everybody knows what E is, correct? It's like pi, it's a constant, it's 2.78 or 718, da, 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 keeps going. All right. So as we look at this one, the cosine as it goes to infinity oscillates, correct? So this one doesn't exist really, right? What's e to the negative 2x? That's the same thing as saying 1 over e to the 2x, right? Because remember that negative exponents just go down to the bottom. As that's going to infinity, this is going to get what? Bigger. So this is really going to 0. So I have 0 and does not exist. So am I going to say the limit doesn't exist? Or does the limit go to 0? Let's look at it. So this one, we're going to use something we did before. Remember the squares theorem? Remember we look at it coming from both directions and it kind of like crushes down? We did a couple problems like that. Let's look at that in terms of this. So I know cosine of x is between 1 and negative, correct? So if I multiply the entire problem that I just did by the e to the negative 2x, I get negative e to the negative 2x. So it's going to be between there and there.
Question.
Yes,
Why is it negative e to the negative 2x?
because I was multiplied by a negative 1. I'm in essence multiplying all three of these by e to the 2x, or negative 2x. So negative 1 times that would be the negative e to the negative 2x.
Oh, okay. Thank you.
I know this goes to 0. I know this goes to 0. So that means that goes to 0. So if you get a problem that kind of looks confusing, sometimes the squeeze rule might help you out, especially on those oscillating ones. Especially when you have those trig functions, and I know it goes between two values. That's when that's really going to be helpful to you. Okay, because I know it's going between negative 1 and 1, and I can multiply it and figure that piece out. You could. Sure. To x, cosine x. That's what it looks like. As we're going this direction, it's getting closer and closer to 0. And relatively quickly. Okay. All right. You should now be able to complete all the homework. I believe all the practice assignments are there all the way through 2.6, so you could actually use those to practice more. My suggestion to you would be while you're going through and doing the homework, have your index card or have a sheet of paper. If you need to look things up, that's what goes on your index card because that's what you're going to need to use on the test. Okay? That's how you study with the index card. As you're looking things up, write it down. I will see you on Tuesday.
One handwritten index card.
One 3x5, 4x6, both sides. Yes, you can use both sides of the index card, but it has to be handwritten. Yes.
You have your handwriting?
Yeah.
How much?
You can write as microscopic as you want as long as you can read it. What's up?
I just want to say thank you for answering my email this morning.
Hopefully, Doc's okay.
I hope so. He had foreign body surgery during winter break.
Oh,
It was in the middle of me taking 2 classes during
oh
the semester.
God. Which is rough because it went really quick.
So he has a type of safety he thinks he's not supposed to. So we got into something that even though we're keeping an eye on him, and so yeah, we'll
So
find
got a
out.
blockage.
Yeah, but like I said, he personally got surgery during winter break, so yeah. Yeah, so I just wanted to let you know in case
No
like
problem.
if you know if like
Yeah.
I'll send you an email if anything happens, but
Their family. Family's important.
yeah.
So hopefully, I have insurance.
No, but thankfully I work out of the office.
Well, that
Yeah.
helps. Yeah.
Yeah.
First thing. So my friend had a dog and had diabetes and everything else, and then cost me like $12,000 on this dog. It's like it was insane. So like when we got our first dog, the first thing I did, I got Trupanion
Yes.
a week before we picked him up, just in case anything happened literally on the way home.
Yes. Yes. No, I tell people that do like Trupanion is especially absolutely amazing because they work really well with vet offices.
Yes.
But like
Yeah, you're like they'll pay directly to the emergency vet that we go to. They'll pay directly to them.
exactly.
So it's like I don't even have to worry about it. It's like they'll send it in. I pay my deductible 10% after that. That's why I said they're like, if something happens, I don't care if it costs me $100,000. Go ahead and do it because the pain is going to cover most of it.
Give me the money back. Yeah.
Exactly. Deal with the dog.
Yeah, and I tell people like if you get a lab, if you get anything that you know, like that's gonna either put something in its mouth and have something happen, or if you know,
Or even a hyperactive dog like tearing an ACL and stuff like those happen quite often
Yeah.
later on in life. It's like those are expensive after a while.
and especially because I think like Trupanion does the thing where it like happens on one leg, they'll cover the other one because that's usually what happens.
Yeah.
Yeah. Yeah.
So
So.
all right, hopefully all's good. What's up?
This is just like, I didn't have time to ask before.
That's
class
okay.
Started, but I was doing like the practice homework and stuff because I was trying to get like, but I don't think I like did any of this. Is this like review stuff that I'm supposed to know?
So these problems, a lot of them were just dealing with slope.
Okay.
So we didn't necessarily do it. We did the ones where we're getting closer and closer to something.
Yeah.
So like if we're looking at just finding slope, you're just taking that point and dividing. So it's the y's over the x's. So it's y2
Okay.
minus y1 over x2 minus
Yeah,
x1.
yeah,
So yeah,
that
that's
makes
basically all they're doing. This.
Okay.
So it's the same kind of concept there. They're just doing the slope. And you're seeing how the slope's getting closer and closer to a point. So we did it with just plugging in numbers. This
Yeah.
is just using a slope to do the same kind
And
of
then
concept.
it's about the secant line.
Yeah, because so basically, so what the secant line is just, so let's just do x squared. We'll just do simple one because I know the answer for this one.
I like looking. I had the same question.
Okay.
I like it.
All right. So that would be a secant line.
Right. Right.
Okay. So as that line gets closer, so you can start to see how it's getting closer and closer. So you can start to see, okay, well, it's right about there. Now, if we zoomed in, that's a tangent line because it's hitting it at one exact point.
Got it. Okay.
Okay. So most of the time it's a secant line because it's hitting multiple points. When it gets to that specific spot, then that becomes that tangent line. So when you're looking for your slope, you're looking for the slope of the tangent because the slope of the secant because it's hitting multiple points. as those points get closer and closer together, that's the limit piece that we're looking at.
So is that why it's telling you to find like the value, like?
Right, at that
before
point, yeah,
and after?
exactly. Yep,
All right.
because you're getting close. Basically, you're coming to doing the limit from both sides. So it's basically the application of those rules that we did in the very first lesson on that 2-2 is like how we're getting closer and closer to both directions.
And then is this a similar concept as well?
Yeah, so the my x is going to be, the point's going to be 5.9 that I'm plugging in.
Right.
That'll give me my x and my y, and then I'm going to use that point with this one to find my slope. So you're going to use the 5.9. So I'll get the answer real quick for it. I feel like- So x equals 5.9, and I would highly suggest using Desmos because it does all the calculations for you. So I'm now going to use that point and the 6, -3 to do my slope. So I would use -3 minus y over 6 minus x, and that's my slope. And then I would change that to 9,9, and that's now my slope, because that's going to be that one. And if I change it to 999, that's now my slope. So you're getting closer and closer. And if you notice, it's getting closer and closer to, in essence, 3.
Okay.
So
Are
your
there-
final answer is like, what do you think the slope is actually going to be? Well, it's going to be 3 because it's getting closer and closer to 3.
And on the like test, do we have like Desmos?
You can use Desmos.
Will we have questions like similar to this?
You're going to have one of those, yeah.
Okay.
So, and if you notice, like using Desmos the way that I'm doing it here is really nice. It actually does
So what-
a lot of the calculations and stuff for you by just changing that one number. So you don't have to constantly go back and do all the calculations out. You can just plug it in here and I'll give you those numbers.
On Monday, would you give us like an idea of what types of questions are going to be on the test?
Oh, on Monday, I'm basically going over the 10 questions that are going to be on the test just with different numbers.
Oh, cool. That's awesome.
Yeah. So you're going to see, that's my reviews. Is basically, here's what we're going to do. This is what you need to study. All I'm going to do is change numbers.
Got it.
So,
Cool.
okay.
Thank you.
You're welcome. And it's going to be similar to the practice, the homework for chapter 2. It's going to be very similar. I think there's 10 questions on there. It's going to be very similar to those.
I wasn't listening to like this part specifically. I get this now, but
Yeah. Same concept.
So,
They're giving you the points. So you're looking at going the directions, each direction for it. So if the point was 15 that, you're going to take that point and find the slope.
oh, okay.
And then that point and that point, find the slope. That point and that point, find the slope. That point, find the slope.
And see where it's approaching. Okay. That
Yeah.
makes sense.
What's up? Are you waiting for? What's up?
I did come in and ask you a question.
That's fine.
So, remember when I told you about?
Yes,
Monday?
next week. Yep.
So I was a little confused. I think I misunderstood. So when can I take this?
I'm going to give it to you the Monday afterwards.
So the next
So-
2 weeks.
Yeah. So you're going to, because you're not going to be here next Monday and Tuesday, or Monday and Wednesday, you said, right? So you will take the test on Monday the 12th.
So okay, yeah.
So I'll have you take the test after class on Monday the 12th.
Is that okay with you?
Yeah, that's fine.
And I
Life happens. Things happen.
I really appreciate
Yeah,
it. I was
it's-
actually a little nervous about
Yeah,
that.
no, life happens. We work on it. My goal is to make sure you understand the material. So
I do. I
me,
actually,
right. So me telling you, oh, you can't take the test or we take points off. It's like, it's not helpful. It's like, I'm trying to figure out if you know it. Like,
no, I
So,
really
yeah.
appreciate that the way you just given us like questions and like work on ourselves. But I actually watch the videos after when I go home,
yeah.
just
Oh,
like to
absolutely. Stop that.
refresh my brain again.
And that's a good
Otherwise,
thing.